Hi everyone. In this lecture we're going to look at how to find the area between two curves. So here's an example. We've got two curves here, this red curve and the blue curve. The red curve is given by f of x equals 2 minus x squared, and the blue curve is g of x equals x squared. We're interested in finding the area of the region that's trapped between them. How do we do this? Well, a first approach may be just to take the ideas that we've had before, where we know how to compute the area of a region trapped between a curve and the x-axis. How do we do that? We just integrate the function that's defined by the curve. So the problem is that we're not finding the area of a region between a curve and the x-axis. We're finding the area of the region between two curves. But maybe we shouldn't let that stop us. Maybe instead what we'll do is we'll look at this region as well, this blue region, and we can say, well, I know how to find the area of the purple and blue region, the region that's made up of both of those. That's just the integral of the function defined by the red curve between -1 and 1. But that gives me too much. I end up getting, in addition to the area of the purple region, the area of the blue region as well. But I can find the area of the blue region by another integral, and then I can take the difference. So that's method one. Method one is to look at the area as made up of, maybe I'll move this over, as made up of two regions. One region is the area under the red curve, from -1 to 1. Take away the area under the blue curve, from -1 to 1. And we know both of these areas as represented by integrals. This is the integral from -1 to 1 of the function given by the red curve, which is 2 minus x squared dx. And we're going to take away the area of the blue region. That's the integral from -1 to 1 of x squared dx. And that gives us the area, what's left over, or their difference, which is the purple region. So that's one way to do it. I want to look at another way to do it. And this other way to do it is more reminiscent of how we approach the area problem in the first place. Now, in order to prepare ourselves for this one, let's just think about the area. Well, it could be, let's say, the first one there. Just that area of the red region. -1 to 1. And I just want to provide a way to think about this integral in relation to that area. Now remember, the idea for computing, or coming up with a definition and hence a method for computing the area, was to slice it up into a bunch of thin little rectangles. Find the area of these rectangles by using the height of the function times the width of the rectangle. Add them all up, take the limit as the number of rectangles goes to infinity, and you end up with this integral here. Now we can look at that 2 minus x squared, that integrand, as just the height of the rectangle at position x. Or in other words, maybe I shouldn't say it's a rectangle anymore. We're taking the number of rectangles going to infinity. Their width goes to 0. These become just little line segments. So maybe I'll think of these as little line segments. So that's a line segment at x. What's its height? The height of that line segment, or in other words, maybe I should say the length of that line segment, is f of x. And that changes as x moves along the axis. And so what this means is that we can think of the area as just the sum of all these little line segments. Okay, well, maybe sum isn't an appropriate word here. Maybe it's the integral of all these lengths of the line segments. And that's exactly what the integral is capturing. It's sort of this generalized sum. It's saying, I've got all these little line segments that, if I glue them all together, I hope to make an area out of those. Well, I can't, because the line segment has no width. It's zero dimensional, so I can't actually glue a bunch of them together in some sense. But not in the sense of the sum, but more in the sense of the integral. The integral is saying integrate over all of the lengths of these little line segments, and that'll reconstruct the area. So the integral can be thought of, or the area can be thought of as the integral of all of these lengths. Dx. That's kind of what we're thinking of. That's what it's a nice way to think about it, because this would then be 2 minus x the length, 2 minus x squared dx. That's the area. Integral of all these little lengths of these line segments. So a dynamic look at that same description. We've got all of these line segments. As we sweep out all these different x values, these line segments sweep out the region in question. How do we find the area? We integrate along the x-axis over the length of all of these line segments. So, can we naturally see now how to extend this when the bottom curve isn't straight? What if we change the bottom curve to x squared? Well, the idea is going to be the exact same. What we're going to do is we're going to integrate over all of the lengths of the line segments that sweep out the region. The only thing that's changed here is to get the length of that line segment at a position x, I need to take into consideration both where the line ends up top and where it begins in the bottom. Before it was beginning at the x-axis. Now it's beginning on the other curve. How do I get the length of the line segment? It's just the difference in the y values on each of the curves. That's our method 2. Our method 2 says, look at a line segment. Integrate over all of the lengths of these line segments as you run along from x going from -1 to 1. So here the area is going to be the integral from -1 to 1 over all of the lengths of those little line segments. What's the length of the line segment? Well, the length of that line segment, the y value of the upper portion is just given by f of x. The y value of the lower portion is given by g of x. So this would be f of x, the upper curve, minus g of x, the value at x on the lower curve. That's at a particular x value. We let the x values sweep out all of the values between -1 and 1. And so the area is the integral from -1 to 1 of 2 minus x squared dx. So there's another way to compute the area of that region. It's to think of it as made up of all these little line segments where you just integrate over all of the lengths of these line segments. Now we get two different approaches for solving the problem. Do we get the same result? Yes, we do. These are equivalent. Why are they equivalent? Well, we know that the integral of the difference, here is our two functions, the integral of the difference of two functions is just the difference of their individual integrals, so they give the same result. Method 2 is a very nice way to think about it, because not only does it naturally generalize from the area trapped between a curve and the x-axis, but it also, in addition to comparing method 1 and method 2, we just have a single integral to evaluate. Method 1 involved working out two different integrals and trying to piece the region up as a difference of two other regions. But this one, we've captured it all in one integral. So let's just summarize what we've done. Suppose f and g are continuous functions and that f is sitting above g. So f is this upper function, g is the lower function. And that happens on this interval a to b. Then the area bounded by those curves is given by the integral from a to b, from the leftmost x value to the rightmost x value, the difference of the two functions. The top function minus the bottom function. Now the diagram on the right here just shows us how we could justify this formula by going back to how we computed areas to begin with. We sliced up a region into a bunch of rectangles. Those rectangles, we just needed to know the heights of each of those rectangles. And in this diagram, we see that the height, so we look at sort of the ith rectangle there. There's our x sub I star. What's the height of that rectangle? Well, it starts down here on the blue curve and it ends on the red curve. It starts on G and ends at F. So the height would be given by f of xi star minus g of xi star. And what's the width? The width is delta x. And remember, our process was to take the product of these two, sum them all up as I goes from 1 to n, and then look at the limit as number of rectangles goes to infinity as n goes to infinity. So that's just this function times delta x, the limit of the sum of those things. And that's exactly what this integral captures. It's the difference of the two functions. So the difference is coming up because we're looking at, in one context we're saying, well, you can think of it as a line segment, but if we go back to how we computed areas to begin with, we use these rectangles. It's the height of the rectangle. Okay, so a nice way to think about the area between two curves is sweep out the region with line segments and just integrate over the length of those line segments as you move along. The lengths of the line segments may change, but just integrate over their lengths. It's the upper function minus the lower function. Let's look at some examples. Find the area bounded by these parabolas. So this is the original example we were just motivated by. Now we're going to actually compute the value. So there's the region we're interested in. I'm going to sketch in one of our little line segments that we're going to integrate over. I need to know how this line segment sweeps out the region. Where does it start from? Where does it end? So it starts at -1, x value of -1. It ends when the x value is 1. And so our area is given by the integral from -1 to 1, what we say integrating along the x-axis of the lengths of these line segments. What are the lengths of those line segments? It's the upper curve, which is our function f, or 2 minus x squared, minus the y value of the corresponding point on the lower curve. So we're at some arbitrary x value. The y value on the lower curve is given by that g of x value. Y value on the upper curve is that f of x value. So the difference in those values is the length of that line segment. So minus g of x is x squared dx. There's our integral we need to compute. So that's 2 minus 2x squared dx. Now we need to antidifferentiate. Antiderivative of 2 is 2x. Antiderivative of 2x squared is 2/3 x cubed. There is a minus sign there. And that's going from -1 to 1. Now we pop our upper limit of integration in and take away the same expression with the lower value, lower limit of integration thrown in. And so this becomes 2 minus 2/3 minus 2, so that's a plus 2. That's a plus 2/3 with the minus on the outside. That becomes a minus 2/3. So this is 4 minus 4/3, or in other words, 12/3 minus 4/3, or 8/3. So there's the value of our area of that shaded region. It's 8/3. And we got it with that single integral. Integral of the lengths of all of those line segments as we move along. Let's have a look at another example. Find the area of the region bounded by the line y equals x, so that's the blue line here, and the parabola y equals 6 minus x squared. So here's our region we're interested in finding the area of. What we're going to do is we're going to imagine a vertical line segment at some arbitrary position x, and we're going to watch what happens as this vertical line segment sweeps its way across the region. How do the lengths change? So here's our area. The area is going to be the integral of the lengths of these line segments as they sweep through the region. Well, the length of the line segment is the value of the top function, which is 6 minus x squared, minus the value of the bottom function, x dx. Now we just need to know what our x values sweep over. Where do they start and where do they end? So I need to know that intersection point, because that tells me where my x values start from. I need to know that intersection point, because that tells me where my x values are going to end. So I need to know the intersection points of these two curves. To get the intersection points, we need to know what x values make the function values the same for a given x value, when are their function values the same? When are their y values the same? That means they have a common point. So this is x is equal to 6 minus x squared, or in other words, x squared plus x minus 6 is 0. Now at this stage, we're looking at a quadratic. We know there's going to be two roots of this thing, if there are any at all. How do we find the two roots? We could use the quadratic formula, or in this case, we just notice that it does factor. X plus 3, x minus 2. And so the roots are negative 3 and 2. So those are our roots. That means this value is negative 3, this x value is 2, and so those are our limits of integration, negative 3 to 2. And so there's our integral that represents the area. Now we can go ahead and antidifferentiate. Antiderivative of 6 is 6x. Antiderivative of x cubed is negative 1/3 x cubed. Antiderivative of x is negative 1/2 x squared. And upper and lower limits of integration are there. Now we pop in the upper limit of integration. That becomes a 12 minus 8/3 minus 4/2, so that's 2. And take away the lower limit of integration as thrown in. So that's minus 18 plus, well, 27 over 3, that's 9, minus 1/2 3 squared, 1/2 9, or 9/2. And what does this boil down to? This is 10 minus 8/3, and that's a negative 9, so that's plus 9 plus 9/2. So that's a 19 plus 9/2 minus 8/3. So common denominator would be 6. So 6 times 19 is 114 plus 27/6 minus 16/6. Oh, that was 114/6. So 27 minus 16 is 11. 11 plus 114, so that's 125/6 is our final answer. So there's the area of that shaded region. So let's look at another example. Find the area of the region bounded by the line y equals 1/2 x, and this parabola opening up to the left, sideways parabola. We want to find the area of the region trapped between them. Okay, so if we're going to apply that same technique, what we need to do is look at the region and see where does the upper curve, where does its description change? So if I scan along, I see that the upper curve is the linear function, and then at some point, at 4 here, the upper curve becomes the other one, the red curve. So the description has to change, which means I'm not going to be able to use that technique I've just used by integrating along the x-axis. I'm not going to be able to use that description or that technique unless I break it up into two integrals. Because as I look at a vertical line segment, I need to know the length of that, and it's going to be different than something over here. This description involves both an upper and a lower portion of the red curve, whereas this one involves something on the blue curve and something on the red curve. So that's fine. It just means that, if we're going to apply that same technique, which I'm going to call method 1 in this case, we just need to split it up into two cases. So maybe our first case is something like this. Find the area of that region. And once we've done that, then we add to it the area of the tip there. And we can work out integrals for each of those and add them up. Why can we work out integrals for each of those? Well, because in each of these cases, the upper curve and the lower curve are consistent. This one's always the linear function, this one's that red curve. Whereas in the other one, both the upper and the lower ones are going to be related to the red curve. All it means is that I really need to know expressions for these things, expressions for these curves in terms of x, right? Because I'm taking a slice, a vertical line segment, at a particular x value. I need to know the values of the endpoints for that x value. So I need to have an expression for all points on this curve in terms of x. So that linear one is not so bad because it means that y is equal to 1/2 x. So for any given x value, I know the point on it. However, for the lower curve, I need to have an expression for y in terms of x. For this curve, there are going to be two expressions. One for the upper curve, one for the lower curve. Maybe I'll write these in red. The upper curve would be obtained by taking this expression, solving for y. And we do that by taking the square root of both sides, but I'm going to take the positive square root. That gives me the upper portion. To get the lower portion, I would take the negative root. And so this lower portion here would be y is equal to negative root 8 minus x. And so our integral that represents that purple region there would be the integral from, well, I still need to know the intersection points, so I'll fill those in a second, from the upper curve, 1/2 x, minus the lower curve, negative root 8 minus x. I'll just make sure that bar extends all the way across, dx. And we're going to add to that the integral of the other region here. And there the upper curve is the square root of 8 minus x minus the lower curve, which is the negative square root of 8 minus x dx. And so there's our area, aside from the fact that we still need these limits of integration. So let's find the limits of integration. They come from the intersection points. How do we get the intersection points of these curves? How do we get these values here of these points? Well, one way to notice this is that x is equal to 2y is another way of writing the expression for the first curve. So if x is equal to 2y, I can plug into the second equation, and that gives me y squared is equal to 8 minus 2y, or in other words, y squared plus 2y minus 8 is 0. And that factors as y plus 4, y minus 2 is equal to 0. Or in other words, y is equal to negative 4 or 2. So y is equal to negative 4 or 2, and we can get the corresponding x values because x is 2 times y. So that would be negative 8 or 4. So we got these values. X is negative 8 or negative 4. And you may say, well, I could have read that off the diagram. Yeah, you're right. I could have read it off the diagram, but the point is I gave you the diagram here. If the diagram wasn't given here, then we'd have to work these out on our own. And so there's our values, which means our limits of integration go from negative 8 for the first one up to the 4. And then for the next one, the little cap here goes from 4 all the way out to 8. And so there is our area represented as the sum of two integrals. Now that's the first method. There is another way to do this. And it goes back to this idea of sweeping out a region with line segments. Here we used line segments, vertical line segments, to sweep out a region. And we noticed that, well, we had to take some care because as we swept out the region, the top curve, the description of it, changed when I went from being capped by the blue curve to being capped by the red curve. But there's nothing wrong with saying, well, rather than letting line segments sweep it out vertically, why not consider line segments that sweep it out horizontally? This is like turning your head 90 degrees and looking at the same diagram, the same shape, and saying, if I turn my head 90 degrees and look at now vertical line segments, once I've changed my head, these are all horizontal. And now let those sweep it out. Why is that a benefit here? It's a benefit because if I look at a horizontal line segment, the left-hand curve is always that blue one. It's always the linear function. The right-hand curve is always the red one. So I don't have to consider two different integrals, two different regions. I can consider just one integral. So there's my region. And here's my horizontal line segment. All I need to know is what the length of that line segment is for a particular, well, what value? Those line segments are determined by their y value. So we're going to be integrating along the y-axis in this case, looking at these horizontal line segments as they sweep out the region moving in the vertical direction, as they sweep through y values, different y values. So I need to know the length of this line segment depending on the y value it's at, depending on what height it's at up the y-axis. That means I need to know the right-hand value, its x value at that particular y value, and the left-hand x value at its particular y value. And do I know that? I certainly do. I know that for a given x value, for a given y value, the x value for this curve is going to be 8 minus y squared. I just take the second curve description and say, if I know the y value, I can work out the x value. I'm just rewriting it, x in terms of y. What about the linear one? Well, the linear one is x is equal to 2y. So if I know the y value, I can work out the x value, and I just need to take the difference of the two x values at a particular y value to get that length. So this length would be 8 minus y squared. That would be that value there at a particular y value. That gives me that value, minus 2y. That's the length of the line segment. So how do I get the area? The area is obtained just by summing over all of these lengths, or integrating over all of these lengths as we move along the y-axis. So we integrate from, I start down here at -4, that's the lowest point, -4. I head all the way up to this highest point of 2. And the lengths of all of these line segments, how do they change as the y value changes? They are 8 minus y squared minus 2y dy. And so there's a single integral representing the area. What's nice about this one is it doesn't involve any square roots. Method 1 involved 2 integrals, both of which involve square roots. This one involves just a single integral. The worst function that appears, the worst in the case of complexity for antidifferentiation, is y squared, which is not really complex at all to integrate. So method 2 is very nice in this case. Let's look at a more formal summary of this. So this is known as doing the calculation along the y-axis, or integrating along the y-axis. That's what we're doing here. We're integrating along the y-axis. So when would you do something like this? Well, you can imagine a region that maybe looks something like this. And we're wanting to find the area of the region enclosed by these two curves and some y equals c to y equals d values. And if you think about doing the integration along the x-axis, we run into a lot of problems here. We need to know the length of a line segment at any given x value. If I go at a particular x value, I see, oh, there's 2 line segments. Already, I'm starting to see difficulties with integrating along the x-axis, looking at the lengths of all these line segments and summing them up, or integrating them. But if I look at a change in perspective, twist my head 90 degrees and look at horizontal line segments sweeping out the region, I see that a horizontal line segment always has a right-hand endpoint given on this curve. Let's call this x equals f of y, and always has its left endpoint given on this curve, x equals g of y. What is the length of this line segment at a particular height y, the length of that line segment? That would be f of y minus g of y. Or in other words, it's the right minus the left. Just like in the vertical case, we do top function minus bottom function. In this case, we're integrating along the y-axis. We do right function minus the left function. So integrating that gives us our area. So let's have a look at that last example again. Find the area of the region bounded by those lines that we already talked about. This is the region we're interested in. If I integrate along the y-axis, so my line segment that I'm imagining sweeping out the region is given by an arbitrary y value, and the y values go from -4 all the way up to 2, then the area, in this case, is obtained by integrating. Y goes from -4 to 2, dy. dy here is important because we're integrating over the y-axis. That's what the y here indicates. We're integrating over the y-axis, or along the y-axis. What is our length of our line segment here? Well, it's the points on the red curve, which are given by 8 minus y squared, x equals 8 minus y squared, minus the corresponding x value for a point on the blue curve, which is x equals 2y. So this is 8 minus y squared minus 2y, and that's what we're going to integrate. So actually I can anti-differentiate it now. It's 8x minus 1/3 y cubed minus y squared from -4 to 2. In other words, it's 16 minus 8/3 minus 4 minus -32 minus, so y cubed, that's 64, -64 plus that, so that's 64/3. Y squared, that would be 16, so that's minus 16. And so it's the difference of these two things, and this simplifies down to an answer of 36. And so we found the area of this region by looking at horizontal line segments sweeping along the vertical direction. In other words, integrating along the y-axis. All right, so that's it for this section. Thanks very much for watching, and we'll see you again next time.